Chapter 5, Helmholtz energy and Gibbs energy. Section 5.3, Maxwell Relations. There are four Maxwell relations, very useful in thermodynamics. Those are the four Maxwell relations that connect pressure, volume, temperature, and entropy together. Now let's look at the first equation, delta T over delta V under constant entropy condition is equal to negative delta P over delta S under constant volume condition. So how do we actually memorize this equation before we can even prove it? Well, it's just if you notice this, the unit of delta T times delta S is the unit of energy. The unit of delta P times delta V is the unit of energy. So you always have Ts on the opposite side and PV on the opposite side. Alright? And also when you do T over V, P over S, pay attention to the subscripts. This S goes here, this V goes here. Now the second Maxwell relation, delta T over delta P on the constant entropy condition is equal to delta V over delta S on the constant pressure condition. The first two equations are less useful than the bottom two equations because it's usually more difficult to hold entropy constant. Usually we can think of adiabatic reversible in which the entropy is constant. However, it's just a lot easier to hold temperature constant or to hold volume and pressure constant. So you have isobaric here, isochoric here, isothermal here, isothermal here. Alright? So now let's look at the bottom two equations which are more useful. Delta S over delta V under constant temperature condition is delta P over delta T under constant volume condition. Negative delta S over delta P under constant temperature condition is delta V over delta T under constant pressure condition. Not only it's easier to have temperature constant, volume constant, pressure constant, these two equations also tell us how entropy changes with volume, how entropy changes with pressure. So this way we can derive or calculate the change of entropy more easily using these two equations, because if you look at the right hand side, I mean this is pretty easy to measure or pretty easy to derive. Same here. The Maxwell relations are useful again because they allow us to predict the less tangible entropy change of a system by measuring the more tangible changes of PV and T. For example, if you can somehow hold the volume constant, you just need to measure the pressure change and temperature change. Do a division, you get this. Before deriving the four Maxwell relations in thermodynamics, let's review some calculus. And the derivation of the Maxwell relations is based on calculus. Here's the calculus. If z is a function of x and y, we can write dz is equal to a function times dx plus another function times dy, and this is f function, this is g function. If the value of z solely depends on the values of x and y, z is considered a state function that depends on the state of z. That's simply the values of x and y. Alright, so if you have values of x and y, the value of z is fixed. And if z is indeed a state function of x and y, then actually there is a relationship between this f in front of dx and this g in front of dy. So again, when z is a state function of x and y, so what does that mean? That means if you're given the values of x and y, the value of z is fixed. Alright? And most mathematical functions have that feature. You can write dz is equal to a function times dx and another function times dy, and these two functions are denoted by f and g, f in front of dx and g in front of dy. Now if x is held constant, dz is simply just g dy. When y is held constant, dz is just f dx. Alright, so these two equations are true when one of the two variables is held constant. Since z is a state function of x and y, we can calculate the change of z when xy changes to x plus dx and y plus dy via two different routes. So again, just imagine, we go from the initial state, which is x and y, to the final state, which is x plus dx and y plus dy. We can go from here to here via two different pathways or two different routes. The first route, we change x first and then change y. In the second route, we change y first and then change x. In the first route, we look at the change of z. The change of z is the change of z in the first step and then the second step. In the first step, we have fxy times dxy. In the first step, y is held constant. Only x changes, so we have this. Now in the second step, only y changes. Alright, only y changes from y to y plus dy. And over here, this is x plus dx. This is x plus dx. There's no change, so we have this equation. Now let's look at the second route. In the first step, we change y. And in the second step, we change x. So we have this equation. And because z is the state function of x and y, so this expression should be equal to this expression. It does not matter which route you decide to take. dz is dz. So this sum is equal to this sum, and then we copy this expression to the left hand side. We copy this expression to the right hand side. Alright, now you can see there's dx, dy, dy, dx. Let's move all the dx to one side, all the dy to the other side. I see this dx here, I see this dx here. So if we combine the dx term together, we get this. I see dy here, I see dy here. We're going to combine this too. So we have this equation. Alright, now both sides divided by dx and then divided by dy. Alright, the left hand side divided by dx, this dx disappears, and then divided by dy. This side also divided by dx and then divided by dy. So we have this equation. And actually, what is this? This is actually, if you look at this, this is just simply the first derivative of y with a derivative of f, okay, with respect to y. So it's just this. It's the first derivative of function f with respect to y. When x is held constant, there's no change here. And look, we have on the bottom dy, that's the change of y. On top, that's the change of f when y changes from y to y plus dy. So this left side of this equation is the first derivative of function f with respect to y when x is held constant. Now let's look at the right hand side. Well, on the bottom you have the change of x. On top you have the change of g when x changes from x to x plus dx. And if you still remember this single variable calculus, it's just dg over dx. If you remember multivariable calculus, we're holding y constant. Alright, so we put y here. This is just delta g over delta x when y is held constant. Now we see the relationship between f and g. So delta f over delta y should be equal to delta g over delta x. And also pay attention to these two subscripts. When we take the first derivative of y with f with respect to y, you need to hold x constant. When you do delta g over delta x, you need to hold y constant. Again, when z is a state function of x and y, there is a relationship between this f and g in this equation. dz is f dx plus g dy. And the relationship is this: delta f over delta y is equal to delta g over delta x. And don't forget the physical meaning of f. F is just delta z over delta x when y is constant. And g is delta z over delta y when x is constant, right? When x is constant, this term disappears, and then g is just dz over dy when x is constant. So this is g, this is f. And because delta f over delta y is delta g over delta x, we have this delta f over delta y is equal to delta g over delta x. Again, this is just f. F is how z depends on x when y is constant. And this part is g. G is how z depends on y when x is constant. Alright, so again, if z is a state function of x and y, if we can determine the value of z given the values of x and y, then we need to have this relationship between f and g. Here's one example. dz is 2y dx plus 2x dy. Is z a state function? So what we're going to do is we're going to take the first derivative of this function in front of dx. This 2y is in front of dx. We take its first derivative with respect to y. We get 2. We then take the first derivative of the function in front of dy with respect to x. We get 2. And this 2 is equal to this 2. Yes, z is a state function. And actually z is simply 2xy plus a constant. Any constant, it can be 3.5 or some other numbers. You can just verify this. You can take the differential of this. You'll get 2y dx plus 2x dy. Now another example problem, 5.3.2. So we have dz is 2xy dx plus 2xy dy. Let's see the state function of x and y. In this case, the answer is no. The first derivative of this 2xy in front of dx, we take its first derivative with respect to y, we get 2x. Now we take the first derivative here in front of dy. With respect to x, we get 2y. 2x and 2y are different. This is not a state function. So given the value of x and y, you're not going to be able to determine the value of z. And there's no way to integrate both sides to get a function for z. No way. Again, when z is a state function of x and y, dz can be written as f dx plus g dy. F and g are functions of x and y. And there's a relationship between f and g over here. Delta f over delta y should be equal to delta g over delta x. Another example, if dz is just 2x dy, is z a state function of x and y? The answer is no, because we don't have any dx term, so f is 0, so we have this equals 0, and then delta g over delta x, 2x over delta x is just 2. 0 and 2 are different. This equation does not hold. Therefore, this case, z is not a state function of x and y. Looks simple, but there's no way to even get a function form for z. You cannot express z as a function of x and y. No way. Now this looks extremely complicated. In front of dx we have this, in front of dy we have this. Really complicated. And then is z a state function of x and y? Surprisingly, the answer is yes. We can verify this. We just take the first derivative of this function in front of dx with respect to y. The result is 2y over x plus 2x times cosine y. So you need to be able to take the first derivative of y squared. It becomes 2y. The first derivative of sine y is cosine y. What about x? X is treated as a constant. Now let's do this part. We're going to take the first derivative of this with respect to x. We copy 2y here. It's treated as a constant. The derivative of ln x is 1 over x. The derivative of x squared is 2x. Now if you compare these two expressions, they are exactly the same. Therefore, z is a state function of x and y, and actually z is y squared times ln x plus x squared times sin y plus a constant. You can easily verify this. Just take the first derivative of z with respect to x. you get y squared over x plus 2x sine y. It's right here. You can take dz over dy, assuming x is constant, and then you get 2y ln x, which is here, going from here to here, and then you get x squared times cosine y you get here. Alright, now we can say the second derivative of z with respect to x and then y is equal to its second derivative with respect to y first and then x. So if you have a state function z of x and y, you can take its second derivative in two different orders. You can take the second derivative with respect to x and then y, or y then x. The result should be the same. In this numerical, in this example problem, this is the second derivative. This is the second derivative. We're just getting the second derivative in a different way. Now get back to thermodynamics. Because u, h, a, g are state functions, and then we can use the differential form of u, h, and g to get the four Maxwell relations. So du is TdS minus PdV. So T is delta U over delta S on a constant volume condition. Negative P is delta U over delta V on a constant entropy condition. Alright, so really we have this T in front of ds and negative P in front of dV. T is the first derivative of U with respect to S. Negative P is the first derivative of U with respect to V. So we have these two equations here, and then we're going to look at the Maxwell relation. We're going to assume the second derivative of u with respect to s and v, and its second derivative with respect to v and s are exactly the same. And on top, this part is simply temperature. On top here, this is negative p, and we have this equation. This is our first Maxwell relation. Now dH is TdS plus VdP. This T is dH over ds if pressure is constant. So we have this equation. And V is dH over dP if entropy is constant. So we have this equation. Now we get the second Maxwell relation by taking the second derivative of H in two different orders. S first and then P first and then S. Left is equal to right. On top over here, delta H over delta S, constant pressure, that's temperature. Delta H over delta P, constant entropy, that's volume. Now we have our second Maxwell relations. These two Maxwell relations, they are correct, but they are rarely used in thermodynamics. It's just hard to hold the entropy constant in an experiment. So here and here. The other two Maxwell relations derived from dA and dG are much more useful. So dA is negative S dt minus PdV, dG is negative S dt plus VdP. From these two equations, we get two more Maxwell relations. Delta S over delta V is delta P over delta T. Negative delta S over delta P is delta V over delta T. These two are really useful, because by measuring this, we can get how entropy changes with volume. By measuring this, we can get how entropy changes with pressure. Now let's prove the last two Maxwell relations. Given dA is equal to negative S dt minus PdV, we have negative S is dA over dt on the constant volume condition right here. And then over here, negative P is dA over dV if dt is 0. So we have this equation. We have these two equations already, and then we will take the second derivative of A with respect to T and then V, or V and then T. Either way, the result should be the same. Delta A over delta T on the constant volume condition. Just copy this here. It's negative entropy. Delta A over delta V on the constant temperature condition. Copy this here. It's negative P. So we get this Maxwell relation. And of course, you can just remove the negative sign on both sides. it's easy to determine delta P over delta T under constant volume condition. For ideal gas, it's just nR over V. So it's really easy. And then we get the analytical form for this. For ideal gas, for a real gas, we can still evaluate this, right? Let's use Van der Waals equation. Delta P over delta T is just nR over V minus NB, right? And even for solids and liquids, delta P over delta T on a constant volume condition is simply alpha over kappa. Both alpha and kappa are constants, so we get a constant for this. So it's really good to have this equation to calculate the entropy change given the volume change. Here's some mathematical derivation. If you have an ideal gas, delta P over delta T is just nR over V, because pressure is just nRT over V. And when temperature is held constant for this ideal gas, we have just ds over dV is nR over V. So ds is nR V times dV. We have only one variable on the left hand side, only one variable on the right hand side. You can just integrate both sides. And then delta S is equal to nR times the natural logarithm of V final divided by V initial. And if this volume of the ideal gas is doubled at constant temperature, we get this equation. The entropy change is nR Ln2. The molar entropy change is simply just R times Ln2. And then we can just plug in R, 8.314 times Ln2, we get 5.76 joule per mole. Alright, when, I'm sorry, there's a mistake here, it's joule per mole Kelvin. And when the volume of this ideal gas is doubled in isothermal process. Now let's derive the last Maxwell relation. Given this equation, dG is negative S dt plus VdP. Negative S is just how G depends on temperature when pressure is constant. Alright, so negative S is delta G over delta T when pressure is constant, right here. V is just delta G over delta P when temperature is constant. Alright, so we have the Maxwell relation. We take the second derivative of G with respect to T and then P, or P and then T. They're the same, so we have this equation. Delta G over delta T on a constant pressure condition is negative entropy. Delta G over delta P on a constant temperature condition is just volume. So going from here to here, it's pretty simple. We just replace delta G over delta T with negative S, delta G over delta P with V. So we have this equation. And it's pretty easy to determine delta V over delta T under constant pressure condition. For an ideal gas, it's really easy to derive. For a real gas, well, it's close to nR over P. For a solid or liquid, this is simply alpha times V, and alpha is just a constant. So it's easy to determine this and then determine this, and then we know how entropy depends on pressure. Now let's look at the example of an ideal gas. Let's say the pressure of an ideal gas is doubled under constant temperature condition. We'll just use this equation, and for ideal gas, delta V over delta T is nR over P. So we have this is equal to negative nR over P, and then we can integrate both sides of this equation, and we get entropy change is equal to negative nR times the natural logarithm of P final over P initial. It's negative nR Ln2. The molar entropy change is negative R Ln2. It's negative 5.76 joule per mole per Kelvin. Sorry about the mistake here. It should be joule per mole and then per Kelvin. When the pressure doubles in isothermal process, entropy decreases. And over here, in this example, because it's isothermal, notice that the volume of this gas is halved. Alright, so you can also use the volume change to calculate the entropy change. It's also going to be negative 5.76 joule per mole per Kelvin. And using the last two Maxwell relations, these two, very useful. We can now derive how U depends on volume and how H depends on pressure under constant temperature condition. So it's very useful. Let's do it. Delta U over delta V under constant temperature condition. du is T ds minus P dV. So delta U is T delta S minus P delta V. Alright, it's just notation. Alright, we have this equation here. We're going to separate these two terms. On the left, T is constant, take T out. It's delta S over delta V under constant temperature condition. On the right hand side, you just have negative P delta V over delta V. It's just negative P. How do we go from here to here? Well, it's just Maxwell relation. Delta S over delta V under constant temperature is equal to delta P over delta T under constant volume condition. It's right here. It's right here. Now let's derive delta H over delta P under constant temperature condition. dH is TdS plus VdP. So we have this. And now this delta P over delta P cancel. So you have V here. You have T. Take T out because T is held constant. T. Delta S over delta P. Copy this. Constant temperature. Copy this. Delta S over delta P under constant temperature condition. What is that? It's right here. It's negative delta V over delta T under constant pressure condition. So we get this. Alright, this is how we derive delta U over delta V and delta H over delta P when temperature is held constant. This too can be expressed as this expression in terms of PVT and this expression in terms of PVT. It's just convenient to measure this or even derive this to get delta U over delta V and delta H over delta P under constant temperature condition. So again, we do a lot of derivations just for the convenience of calculations, derivations, or experimental measurement. Alright, we cannot do this directly, so we use mathematics to prove this is equal to this, and then we determine this either experimentally or mathematically. Same here. It's very hard to determine delta H over delta P under constant temperature condition, whether you do experiments or theoretical stuff. But over here it's easy. Experimentally or analytically, you can easily determine delta V over delta T under constant pressure condition. For ideal gas, it's simply NR over P. For solid or liquid, it's simply V times alpha. For a real gas, we can make approximations. This is awfully close to NR over P, etc. Again, for an ideal gas, now we can prove that U and H only depends on temperature. Delta U over delta V on a constant temperature condition, it's this. T times delta P over delta T minus P. Delta P over delta T is NR over V, and we have NRT over V, that's its pressure, minus pressure, that's 0. Delta H over delta P, well, it's just volume minus T times delta V over delta T on a constant barrier condition. And over here, delta V over delta T on a constant pressure condition is simply NR over P. So we have V minus NRT divided by P. This part is also V. We get 0 in the end. Alright, so it's now possible to derive delta U over delta V on a constant temperature condition and delta H over delta P on a constant temperature condition. This equation and this equation hold true for all substances. It's just for ideal gas, this part cancel, you get 0. For ideal gas, this is canceled, you get 0. Alright. For a real gas, these two are non-zero. For a solid or liquid, these two are also non-zero. But now with these equations, it's pretty easy to determine these two terms either experimentally or analytically.